Before we speak about the event horizon, it helps to let go of the idea that it is a thing you can touch. It is not a wall. It is not a surface. It is not a physical edge made of matter. The event horizon is something quieter than that. It is a boundary in space-time itself, a place where the future changes direction. To understand why such a boundary exists, we begin with gravity again, but this time not as a force pulling objects together, but as a geometry. According to Einstein's theory of general relativity, gravity is not something that reaches out and pulls. Instead, mass and energy curve space-time, and objects follow those curves naturally. Planets follow curved paths around stars. Stars move through curved regions of galaxies, and when enough mass is compressed into a small enough volume, the curvature becomes extreme, so extreme that all possible paths forward point inward. This is where the event horizon appears. The event horizon is the distance from a black hole at which the escape velocity becomes equal to the speed of light. Light is not special because it is fast. It is special because it is the fastest possible signal. Nothing can move faster than light through space-time. So when gravity bends space-time so deeply that even light cannot find a path outward, escape becomes impossible. This does not mean light is being pulled back like a rope. It means there are no outward paths left to take. Every possible future leads inward. This is the meaning of the event horizon. It is not about force. It is about fate. Outside the event horizon, you can choose paths that lead away. Inside it, all paths lead deeper. From far away, the event horizon seems calm. There is no glowing ring, no visible surface. If the black hole is not actively feeding, space around it can look almost empty. But appearances are deceptive. As something falls toward the event horizon, its experience and the experience of a distant observer begin to separate. This is one of the most important ideas in black hole physics. From the point of view of someone far away, watching safely from a distance, time near the black hole appears to slow down. This is gravitational time dilation. Clocks closer to strong gravity tick more slowly compared to clocks farther away. As an object approaches the event horizon, this effect becomes extreme. Signals take longer and longer to reach the outside universe. Light becomes more stretched. Its wavelength grows longer. Its color shifts toward red. This is called gravitational redshift. To the distant observer, the falling object never quite crosses the event horizon. It appears to slow and fade and freeze. Its image becomes dimmer and redder until it disappears into darkness. But this is not what the falling object experiences. From its own perspective, nothing special happens at the event horizon. There is no sudden jolt, no flash of energy, no physical barrier. If the black hole is large enough, tidal forces at the horizon can be small. The crossing can feel uneventful. This difference in perspectives is not an illusion. It is a real feature of space-time. Both viewpoints are correct. This leads to a deep idea called black hole complementarity. It suggests that no single observer can see all aspects of reality at once. But physics remains consistent for each observer. The event horizon separates not just regions of space, but regions of information. Once something crosses the event horizon, information about it can no longer reach the outside universe. This raises one of the greatest puzzles in modern physics. What happens to information? In quantum mechanics, information is never destroyed. States evolve predictably, even if unpredictably to us. But black holes seem to erase information. Anything that falls in appears lost forever. This contradiction is called the black hole information paradox. For decades, physicists have debated this quietly but intensely. Stephen Hawking once argued that information truly is lost in black holes. Later, he revised his view. The modern consensus leans toward information being preserved, but encoded in subtle ways. Some theories suggest information is stored on the event horizon itself. This idea is called the holographic principle. It proposes that all the information contained within a volume of space can be described by data on its boundary. In this view, the event horizon is not empty. It is a kind of cosmic memory. Every particle that falls in adds information to the horizon, not in a classical sense, but in quantum correlations. The horizon becomes a record. Though scrambled beyond recognition, Hawking radiation plays a role here. Near the event horizon, quantum fluctuations create particle pairs. Normally, these pairs annihilate instantly, but near the horizon, one particle can fall in while the other escapes. To an outside observer, the black hole appears to emit radiation. Over immense timescales, this radiation carries away energy and possibly information. If this is true, then the event horizon is not merely a one-way door. It is a filter, a slow translator between inside and outside. However, this leads to another puzzle. If information escapes through Hawking radiation, and nothing special happens at the horizon for the falling observer, how can both be true? Some physicists propose the idea of a firewall, a violent region of high-energy particles right at the event horizon. This would destroy anything crossing it, preserving information by preventing smooth passage. But this contradicts general relativity, which predicts a smooth horizon. The firewall paradox shows us something important. Our theories are incomplete. General relativity works beautifully on large scales. Quantum mechanics works beautifully on small scales. But at the event horizon, they collide. The event horizon is where our understanding thins. This is not a failure. It is a frontier. Event horizons are not unique to black holes. Cosmology has them too. Because the universe is expanding, there are regions so far away that light from them will never reach us. They lie beyond our cosmic event horizon. This reminds us that horizons are not objects. They are limits of connection, limits of causality, limits of what can influence what. In this sense, event horizons are everywhere. They are woven into space-time itself. Returning to black holes, we can consider what happens just after crossing the horizon. Inside, radial distance becomes time-like. This means moving inward is as inevitable as moving forward in time. You cannot stop. You cannot hover. Every second brings you closer to the center. As you fall deeper, tidal forces grow. Space stretches unevenly. Atoms elongate. Molecules break. Structures dissolve. This is not instantaneous. It depends on the mass of the black hole. In supermassive black holes, this process can be gentle at first. In smaller ones, it is violent almost immediately. Eventually, all known descriptions fail near the singularity. The singularity is not necessarily a physical point. It may represent the breakdown of our equations. Some theories suggest space-time continues in a different form. Others suggest the singularity is replaced by quantum structure. Loop quantum gravity suggests a bounce. String theory suggests extended objects. We do not yet know. What we do know is that the event horizon is not the end of science. It is where science becomes subtle, quiet, mathematical, deep. The event horizon teaches us that reality depends on perspective. That time is flexible. That space is dynamic. That information matters. It reminds us that the universe is not built from solid things, but from relationships, from what can influence what. As you listen now, your thoughts can slow. You do not need to solve these puzzles. You only need to let them exist. Black holes are not rushing. They are not urgent. They wait, just as the universe waits. The event horizon is not a threat. It is a boundary of knowledge. And boundaries are where learning happens. You can rest here, at the edge of understanding, breathing slowly, letting gravity hold the stars in place, letting time stretch gently, and knowing that even in the deepest darkness, the universe is lawful, quiet, and profoundly calm.